Yep.
Perfect. So, hello guys, my name is Hussein. This is our weekly seminar presentation. Today we will be talking about, we'll be talking about Markov Decision Process for Curricular Analytics. So we have already submitted a paper for International Conference on Machine Learning and Application. This is my first co-author paper, and it is, first author is Ahmed Islam. He's on the call already here. So we'll go quickly through curriculum complexity and Markov decision process, like briefly. And then we'll start discussing the problem and see our case study for this kind of model, and how we design our experiment, and finally the results and future work. So what's curriculum complexity for the people who doesn't know this? Like quickly, there are three terms that we need to understand, which is blocking factor. Blocking factor is how many courses that a specific course you have to take to unblock other courses. So for example, you have to take physics, so you'll be able to take EE 102 and EE 105 and all of these 4 courses. So this is a blocking factor for each course. The delay factor is the longest path for each course in a curriculum. So it's the intuition about it, like how many courses in sequence you have to take in order to fulfill this curriculum. So for physics, so you have to take 101, then 102, then 105, then 103. So these long path is the delay factor. Complexity is the summation of these two, and the complexity of all curriculum is the summation of all complexity of each course. So let's talk briefly about Markov decision process. So Markov decision process is one of the reinforcement learning models. So we have an agent and environment. Agent is interacting with the environment to learn and take actions. So agent becomes in a state that's sent by the environment and returns, and the agent decides which action to take while he is in this state. And then the environment, so the agent will be in next state, and the environment reward the agent with a reward. So this is like the basic process of Markov decision process model. So it's you are in a state 0, then you take action and you get rewards, and you transfer to state 1. And it's the same. Then you are in a state 1, you take action 1, and then the agent gets a reward, and you become in a state 2, and that's it. So this is a Markovian property in this model. So what does it mean? It means like you are in a state and you don't need to know the previous states. You actually have all information on your current state, so you can know the probability of next state. And it is here as
no memory.
Yeah.
Yeah, just one. Okay.
So
first order.
Yeah. So other notations or terms that we need to understand, like just briefly. So we can define a Markov decision process by state, action, and rewards. This is how you define a Markov decision process, and you need to understand the dynamics of the Markov decision process. What does it mean, a dynamic? The dynamic is what is the probability of you are being in a state and taking an action of this. What's the probability of being in next state, which is S dash, and getting the reward R. So this is the dynamic of the system, how the agent, or the dynamic of the environment and how the agent is interacting with the environment. Last thing is the policy. The policy is the distribution over action for each possible state. So if we have a multiple possible action while you are in the state, this is the policy is which action to take, the probability distribution of this, of action over these, of actions over this state, like the state you are in. So these terms are important to understand. Like actually, what is the action you are taking? So the goal of using Markov decision process, the goal of the agent is, this is making, okay, anyway, the goal of the agent is to gain the maximum reward most of the time in Markov decision process. So each time the agent goes towards, like, wants to have the more rewards while he's moving in the process. So let's talk about our problem. So what we claim is the reduction in complexity in a curriculum will improve graduation rate. This is what we claim. We have. There are many papers, many statistics that Dr. Heilman worked with Ahmed as well, like to prove that. And so what is the problem here? So university, we say to the universities, let's go and change complexity of the curriculum. So they can't see the impact. To see the impact, they have to wait 6 or 6 years at least, or 7 years to see how much is the graduation rate after we change the complexity, which is like a long time. So our aim in this paper is to propose a simulation that examine the modification in curriculum pattern that will improve graduation rate. So basically, we want universities to do what-if analysis. What if we change the course and the structure of the curriculum for a lower complexity? So let's go through this a little bit in detail. This is our model. So we model the curriculum as an MDP and to simulate students' progress through this curriculum. So our state is the path additional to the initial state. So for each state, if the student is here, it means like it passed calculus 1. If the student is here, it means that the student has passed calculus 1 and calculus 2. So, and here is the same for each state. The action is what the student is taking, and if it's pass or fail. So the students can take calculus 1 or physics 2 or both. And it may drop out, like it may drop from the program completely. So these are the possible actions for each state.
So that PF means they passed Calc 1 and 2, but they failed
Physics 2. Yeah.
Okay, got it.
So our policy is probability distribution of students over the action. So this is what we say. So this is the policy, our policy distribution. And because we identify the policy for actions, now we can express this Markov decision process as a Markov chain just to do our calculation and have it. And so we can identify or determine the transition matrix for the Markov chain by having the policy and probability of transition. So our method was for each policy, so which is the red arrow, we have it equally distributed. And for pass or fail is like 0.7 pass and 0.3 fail for each course. So to understand that the student is in this state, or to calculate that students in each state by using this formula, the probability of the Markov chain formula. So our experiment was to to simulate the curriculum, but we have a problem. The well-known problem of Markov Decision Processes is exponential growth of a state for each term. Mm-hmm. So just let's assume we have a kind of a curriculum that the student can only take 2 classes a term. So if we start to expand the possible states and possible actions for each state, the curriculum or the Markov decision process to module the curriculum will expand exponentially until imagine how many states we are, and this is only 2 courses per semester. If we have multiple options, it will be very a huge number of states until we graduate. So what we our proposal was, and this is because of most of the students, if they enter a program, they flow with the same pattern of courses. So we take the most important courses in these classes, and just as a proof of concept, we simulate this model into these 2 curriculum, and we assume if someone is completing this curriculum as graduated. So we have a 35 complexity for the first curriculum, and let's call it degree plan, and the second one is 25 complexity for this. So here is the model for this one. So students is moving from a state to another state because it does not have a lot of options. And here is the MDP for the second curriculum or degree plan. And so let's take one example just to explain how we are doing it. So if a student is here, he already passed Engineering 101 and Calculus 101. So there is a 25, there's a probability of 25% or 0.25 it's taking central courses, and 0.5 taking Calculus and central courses together, or 0.5 to take Calculus 2. So these are equally distributed. And for passing a class or failing a class, like 0.7 and 0.3. And so here is the policy as mentioned in this notation here.
So that policy means there's a 25% chance that if you're
in a state NG 101 to try to take action and go to calculus
next.
So I take action of taking
okay.
Calc 101.
Okay, got it. I got it.
So yeah. So this is the results we have. So this is the semester, number of semesters that students traverse through. And here is number of percent of a graduation rate. And we found that for the original curriculum, which has a complexity of 35, and here is we see a better graduation rate for students who like the simulation for the lower complexity.
This is for the improved curriculum is the one where you.
Yeah, have lower complexity.
But it's the one where you change how you do circuits?
Yes, exactly. So here is.
Oh, it's that one. You're just doing the curricular pattern. Okay. So
just the curriculum pattern.
Just this piece of it.
Exactly.
Okay.
Just as a proof concept of that the model is working.
Okay, got it.
So
let me see that curve again. You're saying just for those, how many courses, 6 or 7 courses?
Yes.
Some people can take 10 semesters to finish.
Yes.
Okay, all right.
Yeah.
All right. We wouldn't let that happen. They'd just be out of the program, really, is what would happen. But that's okay. That's
So what we should get a curve like that.
Yes.
For if it's like
yes. This is because they're attempting Calc 1 6 times or something.
So that gives us a feeling that our model is working because the curve should make sense. So here is, so we introduce a dropout state.
Oh, there you go.
So when there is a possibility a student can, like this is the actual reality, like we have a drop. So we add a state of a dropout and we got this result.
Okay.
So now we have a better, like this is with the dropout and without the dropout. This is the original curriculum. So the blue one is without the dropout states, and the red one with the dropout states. So for validation, we validate with Monte Carlo, if you remember the Monte Carlo model. So what we do is we have a Monte Carlo process to simulate many students, and then we take the average.
Okay.
So we got exactly the same results, almost. So the dots are from the Monte Carlo simulation, and the lines are from our MDP simulation. And that's what gives us a feeling that our work is so this our model and simulation tool is working properly. So before discussing future work, anyone has any questions? Do you think anything you want to say about it before discussing like future work?
I just have one quick, simple question. How do you do the Monte Carlo simulate? Like, how do you sample the actions? Because you need an action for transition. Is there a policy or?
For this one or for the Monte Carlo?
For the Monte Carlo. For the Monte Carlo.
Yeah, Ahmed, can you explain this? Because I talked to him yesterday about it. So.
If it's not a quick answer, we can skip.
No, it's okay.
Ahmed, are you there?
You are in mute.
Yeah. Sorry, can you repeat the question? Is it about the Monte Carlo or how?
Yeah. So to do the Monte Carlo, I'm assuming that you sample you start at an initial state, you sample an action, and then you sample a transition given the state and action. So my question is, under what policy are you sampling actions for the Monte Carlo?
Yes, definitely. So basically, we adjusted the policies and we make it deterministic. That is, we assume that with a 100% or probability of 1, the students can take 2 courses at a time.
Okay.
So basically, those 0.25, 0.25, we excluded those, and it makes more sense.
That makes sense. Thank you.
Yeah, definitely.
Yeah. And anyone have any other question?
So the lines are analytic and the dots are simulation.
Yeah.
Got it, okay. So closed form, you compute it from the model.
Mm-hmm.
Okay, got it.
Yeah, this was like the main intention. The main intention when we started working on curricular complexity, like a master student at UNM, he basically came up with Dr. Han. They came up with the Monte Carlo simulation, and the main motivation was at that time if we can come up with a closed form solution. That was the main motivation of this work. I mean, yeah, and that's why we ended up basically trying the MDP on these small patterns. Yeah, that was the main motivation in closed form.
Okay, yeah, that's good.
Okay, for future work, Ahmed suggested two things in the paper. So it's not like, because I think more important is the pattern of a curriculum than a full curriculum, because there are many electives and non-connected courses.
Yeah, so yes.
But I mean, we still suggest to do a full simulation for a full curriculum. We need to solve the problem of a huge number of states. Our suggestion is to construct the MTP using historical data, and because our assumption that students usually take the same pattern of courses, there will be many reduced number of states, because I mean, if I start me and Yeming in the same year, most likely I will have the same take similar courses. So we'll have a lower number of states. We suggest also to reduce, to eliminate this data or restrict this data to 1 year, maximum 2 years, to avoid changes in programs and curriculums, so we don't have a crazy number of states. And we hope we get a good result. And then we label these electives. So for, let's say, humanities and art and something like that, we have only one label or one name for these courses, or we can call them elective 101 for all electives, elective 102 for the second type of elective. So this is how. So we label equivalent courses
to reduce the number
of states. So maybe I'm taking English 102 and he's taking English 102B, which are technically the same classes, but so the idea is to reduce number of states.
What software for computing for the MDP? What is it that you use?
I mean, for this particular paper, we used R.
Okay.
But I'm trying to make it into Juliet in our toolbox.
Okay.
But yeah, it's part of
Okay.
So that's what I'm trying to do, full simulation in the toolbox.
I see.
And the toxicity. So another thing, Ahmed, has it is in the paper. Let me just so we want to identify the toxicity of courses. So what is toxicity of courses is, let's say someone has already passed A, B, and C, D courses and wants to take, for next semester, wants to take course E and course F. So our suggestion for so what we want to say about toxicity, does it make a difference for students to take these classes together or apart? So our suggestion our proposal for measuring toxicity is to simulate the same Markov Decision Process model, having these classes taken together and see the graduation rate for these, and then take them out and make them apart. And we compare the graduation rate for both situations or both models and see what is the difference. This is for future work. And I mean, this is our proposal for these two ideas as a future work for this paper.
So something to account for. So you've got E and F together here. E has an impact on your grade in F, and vice versa, F on E, and they may not be the same.
You are right. I mean.
Okay.
So you are.
That. Yeah.
So maybe I should have another state saying, if I'm taking F, then E.
Well, that's one thing, but also just the toxic impact of E on F may not be the same as the toxic impact of F on E. So in other words, I put them together in one term, and my probability of passing F may go up or down, and my probability of passing E may go up or down by a different amount.
So here, okay, I got your point.
Yeah.
So you are talking about
they're not symmetric. It's not symmetric,
okay.
And we see that in student data.
Okay.
Like the one calculus together with physics in the first term, the impact is of physics on calculus is stronger than calculus on physics.
Mm-hmm. Interesting.
Yeah.
So that I understand your point. You want to see the impact on passing for this specific course.
When they're together.
When they're together.
Yeah.
But the model is capturing only graduation rate.
I see.
I mean, we can maybe have this to see the next state of. So if
So what is your toxicity measure going to look like when you what is it going to be a probability when you put the two together? There's some probability that.
So the probability of graduation if you take these together and probability of graduation.
Yeah, that's different. Okay.
But I think we can still capture the pass rate for each course in the next states, but this is like a bit like.
Yeah, I see.
Yeah, we can have this.
Okay.
Because we are.
What you'll do is you'll just look at its impact on completing the sequence.
Completing the sequence, but we can still see the impact on next state.
Okay.
Like if it's both, so did the E and F, did the student pass E and F or E only or F only?
I got it. Okay.
I mean, we can do that. Someone is, okay. I think I'm done with my presentation. I appreciate your feedback, and if you have a question, you can ask. If you have any feedback, you can send it to me, and if you have, you can say it here or send it to me by email or by anything.
Anyone have any questions or comments?
I can put my email here, and this is recorded. You can stop the recording. This will be recorded, and if you want to see it again, you can see this.
Actually,
the paper. Okay, Ahmed, go ahead.
Yeah, I was just going to say that it will be interesting if one of the students, masters or PhD student, can do a simple GUI, that people can play with, and automate the process of building the MDP. If somebody, I don't know, instructor, faculty, administrator, they just draw a pattern, a small pattern, like a limit with a limited number of courses, then behind the scene we can automate the building an MDP for that. I think that will be interesting just to play, like the instructor or the faculty can play with the policy, can play with the pass-fail rate, dropout rate, whatever, and see how this would impact, or play with the complexity. And I think it will be a kind of cool tool to include.
Yeah, so you would create a graph, and then it would create this
simulation.
Yeah.
But they would create that graph as.
Yeah.
And then you could.
Yeah, because it can be automated. Definitely, it can be automated. Building the MDP instead of doing it manually as we did in our paper. We did it just for the proof of concept. But if we can make it as a tool, that will be exciting as well. Especially that it's a closed form. It's not gonna take a long time doing the simulation.
Yeah.
But you still have to enter all those transition probabilities someplace, yeah.
We assume in this,
Oh, you make, okay.
and like Ahmed is saying, we assume it's equally.
I see.
So
Okay.
the only pass rate and fail rate,
Yeah.
if a faculty want to see the simulation in a curriculum pattern, yeah, right.
Okay. All right. Well,
I
I can stop there.
question. Yeah,
Yeah.
I have a question. Or maybe a comment, I'm not sure. I think I like that you're using historical data, student patterns to kind of set up policy, but I don't know that students' choices of courses they take are optimal. And I think down the road, this would be really a neat thing to use simulations to try to optimize what the strategy should be for advising students on what courses to take next. I don't know that we're optimized in that regard already, and I think simulations have some real potential to extract that out for improving our advising processes. So really optimizing the policy rather than just fitting to what students are already doing. Is that something that you're thinking about also?
Yeah, I think in this case, Hussein, you should probably next time or in the following weeks, you should start presenting the personalized degree plan that we worked on, because it kind of captured what David is mentioning. The idea of the personalized degree plan is to tell the student what courses to take in each semester based on the student criteria and characteristics, like demographic characteristics or competence level. I think that might be helpful to maybe present at one point, because kind of it crosses with the MDP.
Yeah, and you just,
sorry,
go ahead,
regarding
Dave.
toxicity, course toxicity, the way I understand it, to use Greg's terminology, is that course toxicity is really an instructional complexity issue that students taking 2 classes in the same semester, it changes the relative pass rates. And what I'm seeing your simulations trying to extract is more structural complexity rather than an instructional complexity or a curricular complexity contribution to toxicity. I expect they're going to be inversely correlated, actually, that the more you might have more benefit to taking, say, high complexity courses early. But if you lump them all together, you might find instructional complexity will kill your pass rates on those things. It's a really interesting problem to think about, those combinations, both in terms of the structure of the curriculum, the performance in the classes and how it changes.
Yeah, you're right. It is kind of mixing them. That's a good point you're making.
Yeah, do you have anything to say?
No, thank you. And then if I real quick, I just wanted to show